Hello. My name is Sergey Bratus, and I'm a program manager at DARPA I2O. And I'm here to talk to you about software and how we need to change the ways we build it, design it, maintain it. In particular, I want to bring forward this idea that we have to go from building software, today we talk about build chains, build tools, to maintenance tools and maintenance chains that do not only build but also maintain. And this is a new concept. We're still living the legacy of the 1960s, 1970s tool revolution that Grace Hopper was a defining figure of. And when you think of that revolution, three things happened. One, the tremendous insight that programming had to be made lucid to humans. You had to use existing talent of humans programming as naturally as they could, with those programs then being translated to the performance-optimized machine presentations. There was another view that you had to program in the language of the machine. And Grace Hopper saw that this was not a path leading to success in building a lot of software or having a lot of people building software. The second ingredient of that tool revolution was automating how software was put together, software composition. Software was already becoming complex enough in the 60s and 70s, consisting of enough parts that you needed what she called a compiler and what we know now as a linker, a means of automatically combining different pieces of software. Again, you can do this by hand. People used to do this by hand, but the tremendous insight was in that you need automation for that composition. And we've done this, and even today, a programmer from 60s and 70s would look at our tool chains, at our build chains, and see familiar pieces, and would recognize almost all of the tools. This is a testament to the staying power of that tool revolution. And we've done great things with it. And DARPA was at the forefront of it. Of course, the internet, the mother of all demos that defined today's desktop experience with the mouse and the desktop as such. Look at a computer playing chess in 1964. Look at specialized hardware to enable reasoning, the Lisp processor, another DARPA project. And of course, from that black and white past, we go to today of computers doing machine translation, not only of language, but of cultural realities and emotions. Look at the autonomous vehicles driving us around, and also about computers protecting other computers, the cyber grand challenge with computers reasoning about software and changing software at machine speed to protect it against cyber attacks. And then, of course, you can ask Siri to order you a cup of coffee. We've been building this capability, and we've achieved amazing results. And we've been building, building, building. Have we been maintaining? And the answer is, unfortunately, no. Nearly not enough. This is just one of the many reports on breaches of computing systems. And you will notice several things here. One, social engineering is on top. And computer scientists, hard computer scientists, engineers, tend to dismiss social engineering. But social engineering actually means that you, the user, and the programmer are disagreeing about what should be happening. We're not great about translating the intent of designers of systems into users' experience, into programmers' code. That's why this venue is so successful. Now, the next one you see here is basic, so-called, web application attacks. Now, we are 20 years from the Bill Gates famous demo that stopped development work at Microsoft in order to facilitate security rethinking of Windows. And it achieved great results in that you see much fewer blue screens of death, memory corruption. The operating system, the programs crashing and just detecting the fact that something bad has happened, memory has been corrupted, they cannot proceed. But vulnerabilities are squishy. They're like a ball under a carpet. You press here, the ball rolls over, now you have another bulge. Web application, basic web application flaws are flaws of memory-safe languages. There is no memory corruption there at all. There is just a string rewriting. And yet, this is an enormous problem. So what you have here is the inability to keep the software maintained up to the intent, up to the changing understanding of its function, and up to the changing nature of the threats. Again, we built, but maintenance is lagging. But can we just ignore it? I mean, we've got such great things. And the answer is no, not at the scale at which this is happening. This is a litany of statistics, each one of which is concerning enough. But of course, you will remember the breach of the pipeline, a major energy system on continental scale, on the national economy scale. Even more concerning, worldwide, we have deaths of patients who could not be accepted at a hospital because its computer system was down. They had to be driven to another hospital, and it was too late. So no, we can't ignore it. Are we learning from our mistakes? The answer seems to be no. Vulnerabilities grow exponentially. So something needs to be done. Something is happening that we have not foreseen. What is it? And to understand the answer to this, we have to come back to the foundations of the tools that we're using. Remember, programming was made lucid to humans, and then translated through many rounds of non-obvious transformations to its binary executable form in which it is delivered. The delivered software is opaque. What that means is that in order to change a piece of software in the deliverable, we have to rebuild the software from source. This is like tearing down a building and rebuilding it anew to redecorate a room. For any other industry, this would raise eyebrows. But for software, because of this emphasis on performance that we had in 1960s and 1970s, and which shaped our entire tool chain, this is the accepted norm. At DARPA, we like challenging accepted norms. What does it mean for the software to be non-intelligible in its deliverable form? It means it's not maintainable. So whenever you see this label, this is bad news for you as a user, a consumer. But in fact, in software, we have a worse situation. There are no developer serviceable parts inside. It's to tear down the building and rebuild and recompile. Now, how hard is it to recompile? So you just hit a button and a bunch of cloud servers do their thing. Not quite, because in this process, a small change in the code does not guarantee a small change in the deliverable, and it does not guarantee a small change in the behavior. In fact, you may end up with a binary deliverable that's nothing like what you started with. That is very hard to align. In fact, a company that delivered a first product that aligned a patched binary versus the original binary was promptly bought by Google. Zynamics was the maker of the bin diff, and it was a flagship of this kind of an analysis. With behavior, it's even worse. If you recompile your software with a slightly different version of the compiler, you might get behaviors due to compiler optimizations that you never observed in testing, that you never observed in integration. That is why, after each small change, you tend to test until your test budget runs out. And that is typically the point at which you convince yourself that your change does not affect the baseline behavior. This is not a good situation, and this is a particularly bad situation for the DoD. This is the 2018 Government Accountability Office report on weapons systems, which found that only one vulnerability in 20 of those found by a previous report a few years before has actually been fixed. Just think of that. What about the other 19? It takes from 6 months to a year to several years to actually patch a known flaw, a known vulnerability. Why is that? We just discussed it. A change in code leads to, or may lead to, precipitating changes throughout the rest of your system and will scrape the hard work that you put in during integration. Therefore, patching is a high-risk activity. Rebuilding is a high-risk activity. That disconnect between building and maintenance and the capability to build versus capability to maintain is something that's really hurting the DoD. There is hope. There has been a mathematical, formal methods revolution that allows one to produce software that is provably, demonstrably free of defects. Clean slate based on formal mathematical methods of desired behavior and proven all the way through the layers that down to the binary, the specification is observed and obeyed, and no other behaviors are present. This has been demonstrated by the DARPA HACMS, High Assurance Cyber Military Systems program created by Dr. Kathleen Fisher at I2O. And the final demonstration of that really impressive project was a Boeing Little Bird, an unmanned helicopter that flew while the hackers were given access to its systems and were doing their best. It was one of the most qualified red teams to break out of the containment to affect the avionics controls, which they did not do, which they were not able to do. So formal methods work. We can't build software that does not have emergent behaviors or behaviors that favor the attacker. This was put to test in DEF CON this year, where the international best of the hackers tried attacking this drone, which had HACMS-derived firmware, and they failed to penetrate it. They failed to steal this drone. So this is great news. And this is a great breakthrough. The issue with this is that so far, it requires a PhD in mathematics and special tooling that requires you to have a PhD in mathematics. So you really need a team of PhDs writing the software. This doesn't scale. And OK, so this looks like calculus, right? You're thinking, this is not so hard. We can do this. Calculus scales. No, it actually kind of looks like this. This is an excerpt from an actual paper that's fundamental to the technique called abstract interpretation, written by Patrick and Radia Cousteau. And granted, this paper was under a severe page limit to get accepted, but this is what it actually looks like. This is something that we need to continue working on despite this demonstrated breakthrough in machine reasoning about code and code composition. See how we're coming back to the origins of our tool revolution? And now, what happens next? What needs to happen next is a revolution in synthesis of the older principles of our tool chains and deliverables, and these mathematical breakthroughs that enable software that can be constructed and constructively shown to be free of faults. So we're going from a demonstration to a vision of software that is both correct by construction and mathematically demonstrable as such, to software that is correct by construction and maintainable for extended periods of time. And if you're thinking, well, 100 years of software, who uses software for 100 years? Unix is coming up on 50. It is very likely that it will stay with us for the next 50 years. So 100-year software is actually a minimum that you would want to have in your infrastructure. But there is a significant ask here that is made of theory. Currently, proofs do not easily translate between software versions and changes. They are not easily portable between platforms. For software, there is no moment of perfection. So proofs must be changing alongside with software, alongside with the maintenance tasks of the software. And that is one of the really important aspects of achieving this vision of a correct by construction 100-year software. That needs a significant change in thinking, and this needs a significant change in rethinking the tools and making the tools available. I'm now going to tell you about a few programs out of ITO's portfolio, just the highlights, there are many more, that try to advance different aspects of this vision. The first highlight is the verified security and performance enhancement of large legacy software, vSpells. First and foremost, we need to address legacy software. We need to be able to bring the software that embodies millions or billions of human hours of qualified labor into the future, into a state of maintainability. But what happens with legacy software is that even in the DoD, when the interface documents are a requirement, when modularity is a requirement, you see paths being introduced into the code and connections being introduced between layers that break that modularity for expediency, to adapt to a change in the environment, but still they are there, and you need to be able to make a connection or falsify documentation versus the real system. vSpells looks to comprehend large legacy code bases, untangle them, bring them back to the state of safe modularity, and then enable replacement of modules with new improved ones. Think a more secure communication module, or think a hardware-enhanced reasoning module, or an AI capability of something that was provided by slower, non-accelerated code before, and then dropping in that replacement into a legacy system without violating its expectations. If you need to be bug compatible, you have to be bug compatible. This is a hard problem in understanding and extracting the intents and the semantics of the code. This is a first-class problem. Many of the kinds that surface when you start looking at actual existing code capital, if you will. Then there is AMP, Assured Micropatching. In many cases, the source code or the development toolchain, the means of rebuilding that code into the binary, have been lost. Or the engineers who understood that code base and could make changes to it have moved on to other assignments. And then you're left with a situation when you know there is a vulnerable binary component, maybe even an open source library, which you understand very well. And that has this really very well understood bug. And yet it's compiled. It's compiled throughout your entire fleet of platforms. And on each one of those platforms, it exists in a slightly different binary form. How do you find that 1 byte, or those 2 bytes, or those few bytes that you need to tweak to fix that vulnerability? Even if the vulnerability, typically vulnerability fixes are small, but you need to find where to apply them. You need to understand the binary. The binary is the ground truth. Today, this is done. This is the process that takes months and usually millions of dollars if you have to do it. And one of the tools that are used are decompilers. You extract the binary, which is the holder of your ground truth. You got it to work through integration, through an enormous effort, and you want to change it the least. But remember, a small change in source code, even if you have the source code, does not translate to a small change in the deliverable. Not with the deliverables and tools we have today. So you want to be changing the binary, keeping as much of it original and unchanged, and yet tracking all the possible impacts that your binary change could produce. We're building tools for this. We're building decompilers that allow you to situate the patch. In fact, this work is being evaluated here at Colorado State. And the testbed for this is a heavy vehicle engine control unit that controls an actual engine from a heavy vehicle. The purr of that engine is one of the most comforting sounds I've heard after the vulnerability has been patched, and the stutter caused by the exploitation of a vulnerability goes away. This creates new kinds of tools that first decompile code for a purpose, for finding the locus of a patch, and then recompile with the knowledge of an existing binary. Your current compilers don't care about your previous binary. No matter how hard you worked to integrate it, it just goes away. We're building assured recompilers that preserve as much of the existing behavior as possible and give you an assurance case, an assurance evidence that the changed behaviors are only those relating to a vulnerability. A hard problem, a fundamental research problem, relevant to anyone with a fleet of devices that need to be patched and can be attacked. Capturing intent is an incredibly important task of any programming language. And remember, this is what started the original tool revolution. What you're seeing here is failure to capture intent. This is the Ariane 5 flight at 39 seconds, at 37 seconds, a piece of code that was meant for Ariane 4 and was not meant to be run on the Ariane 5 at all, has been run, caused an integer overflow that was caught by the rocket systems, but it didn't know what to do with them. So it self-destructed. It initiated the self-destruct, taking with it about $370 million. A small bit of annotation in the right place would have caught this. The intent-defined adaptive software, IDAS, is looking into ways for programmers to provide such annotation in a non-burdensome manner. And then there is the need to change the actual software or systems engineering process. From software, we go to systems that comprise both software and hardware. And this is the Cyber Assured System Engineering case program. One thing to observe about the current practice of systems engineering is that they're driven by requirements. Those tend to be positive requirements. The system shall do X, Y, and Z. Then the system is built and tested, and we want that system to be cyber resilient. Unfortunately, cyber resiliency requirements are negative, not positive. They are shall not kinds of assertions. The system shall not do any of the following, no matter what the environment, no matter what the input, no matter what the attack form that may be coming at it. What we have today is the situation when a system is built, tested, and then has to be rebuilt because it fails some of those cyber resilience requirements. CASE seeks to bring those non-positive requirements into the early stages of the system's design, changing the systems engineering process and equipping systems engineers with tools to express their intent with regard to cyber resilience. We're hopefully going away from the situation when we close the loop for cybersecurity after the system has been completely built and is ready to be tested. Another program that supports this and expands this is the Automated Rapid Certification of Software, ARCOS. Assurance evidence that we have today applies to whole systems. We do not have automation for linking up assurance evidence as we link up software binaries, software deliverables, code. Again, think of the linker, but for proofs and assurance evidence. ARCOS aims to take this compositional approach and create the tools for composing your assurance evidence, be it proofs, be it testing, of the many components of your system to reduce your time to the authority to operate, or ATO, translating to more rapid changes, deployments, capabilities. This is, again, a hard problem, a hard mathematical problem, an array of hard mathematical problems that are surfacing from the needs of today's complex systems in the DoD to the first class of fundamental computer science research and first-class tools that are on par with compilers and linkers. In fact, you can think of it as a linker for assurance evidence in the Grace Hopper sense. And so here we are. We are looking at the future in which software can be automatically reasoned about and maintained after it's been delivered. And of course, you have the software bill of materials requirement in the 2021 presidential order on strengthening the nation's cybersecurity, which says that, among other things, delivered software must have a list of its components and its provenance. I posit that this is a great start, but this is not enough. Because as we all know, a system is more than a sum of its parts. We want to expand on this concept. We want to expand on the idea of the software bill of materials to reason about those compositions of components that are more than the sum of those components, more than the sum of the parts. And this brings hard mathematical questions, hard computer science questions, hard tool building questions. And so in the future, you could think of a new foundations of tools that have not just compilers and linkers and loaders that take today's deliverables and run them, but also metadata created and packaged along such as the software bill of materials, but also proofs and any partial reasoning results saved by the compiler and the linker, which allow you to rerun that reasoning as a customer, avoiding breaches such as the SolarWinds, in which the attackers did not touch the code. They compromised the build system. And they injected the payload and the remote access Trojans into the deliverable without touching the code by simply compromising how that source code was built. So we'll go from those kind of systems, those kind of tool chains, to tool chains that also include automated patchers that can reason about patches, recompilers that transform software and automatically move it between platforms just as they move patches between the different compiled versions for different platforms, and relink software and reason about results of recomposing it. Completing the loop, combining the two revolutions, and going from building and not maintaining, from build chains to maintenance chains that maintain software and adapt it and transform it as needed. And we are at the third stage of that revolution. We are combining the old and the new. We're combining the foundational insights and the new mathematical breakthroughs. And we have a number of programs doing that, looking to hide the math, looking to fold the math into tools usable by regular software developers, and to make shipped software maintainable. It's fundamental computer science, too long ignored. Please help us surface those problems, solve them, and apply them to your use cases. Thank you. I think we have time for questions. I'll move over to see them. How do we know that engineering more security into software systems, as you describe them, will be cost-effective and won't cost more than it's worth? We do know, because what is the biggest expenditure in development of code? It's debugging. It's finding that the system, as you built it, does not follow your intent. Hundreds of hours for any given module are spent on debugging it. Then comes the testing. The testing is even worse, because now you do not have your intent ready to hand. You are dealing with behaviors that surprise you. And it gets even worse in integration. Integration could take months. Integration damages everything that you designed so carefully and documented so carefully, because you have a myriad of changes being applied during that fun time. And are they all reflected in the final documentation? They're certainly there in the software. So this approach would help you avoid or eliminate most of those delays. The biggest expense is programmers' time misspent, followed by testing time. Cutting that would be a huge cost saving. Is it possible to engineer software systems to resist attacks and attack vectors that have not yet been imagined by designers and/or hackers? In fact, we're working on this. We're going from the view of exploitation as just another clever trick or another clever set of tricks that somehow got overlooked by designers, to the concept of emergent execution, emergent properties, emergent computation. Systems as built provide the attackers, as it turns out, with building blocks for their attacks. In fact, those building blocks are stable and reliable because they're engineered to do so, to be so. They're just recomposed by the attacker in ways that were not anticipated. On a program that will be kicking off this fall, Harden, we're looking into the concept of emergent computation and denying it to the attacker. This is exactly about suppressing the capability of the attacker to adapt pieces of an existing system, a hallmark of today's exploitation, contrary to the intent. Do you see a role for AI and machine learning in engineering software secure software systems? For example, learning about vulnerabilities from well-studied software systems and applying that knowledge to automatically discover flaws in the new systems. Yes, we will have to do this. This is pretty much a given that we will need automation to comprehend software, understand its emergent behaviors, transform software, whether to eliminate flaws or emergent behaviors, or simply to move it to another platform. This is human knowledge that is teachable, just as attacking is, that has its own structure and ways of transmission. We can pick up a lot of that and train AI systems to provide that automation. So it is absolutely a role for AI, perhaps the third wave of AI, because we're not talking about statistical phenomena here. We're talking about statistical and symbolic phenomena. Exploitation, as we've been demonstrated again and again by the attackers, is a well-teachable, reliable process. We must counteract it with automation that learns it and denies it. Modern cloud software platforms are updated with new code around the clock without a complete rewrite of the code. Does this new methodology speed the delivery of code updates to distributed endpoints? Well, yes. I mean, we're talking about IoT and cloud operating in conjunction. Of course, what that brings to mind is the plight of a particular company making heart monitors that were processed by cloud servers and that found themselves dead on the bodies of the patients as the cloud servers were taken by an outage of a particular data center where they operated. But I think there is a bigger question here. Does the modern cloud delivery model improve security? Not necessarily. Emergent behaviors are not necessarily eliminated by delivering more and more code or delivering code faster. In fact, this is the ball under the carpet kind of thing. And in fact, in modern cloud platforms, as has been demonstrated at the recent Black Hat conferences last year and this year, you find exposed, exploitable, borrowable, reusable functionality that serves as an amplifier for the attacker. So cloud software needs to be understood with respect to those emergent behaviors, and it needs to be understood now. It is an urgent need. And we do understand what buffer overflows do. We do understand the Ariane 5 kind of flaws. Do we really understand the modes of flaws at scale that could happen in a cloud system? I think the answer is maybe not yet. There is a new science of it. And, well, we're on it. Similar to adaptive control and feedback system theory used in flight dynamics, could a similar idea, that of an integrated and adaptive feedback system, be implemented into legacy code to better track source code changed and their effects in the deliverable? Most likely, yes. I invite you to look at the IDAS program that tries to incorporate some of these ideas into its implementation of intent. But generally, ideas from physics, ideas from control theory, have been neglected by software engineering for perhaps too long. And if anything, we need more mathematics of the well-understood kind in our software. And composing it, combining it with the symbolic systems that we have now is a hard problem, but it is perhaps a fruitful direction to explore. Can we switch to interpretable languages like Python or Perl everywhere, since programs written in interpretable language are both the new norm and easily patchable? Are they easily patchable? I think that the analysis, the static analysis of a system that is written in a memory-safe language can be just as challenging as the old C, with the proviso that we already know how to look for those flaws in C, and we don't yet know how to look for those in interpreted language. Case in question, JavaScript. It's in your browser. It's not in my browser because I turn it off. It breaks half the web. JavaScript has been the attacker's way into browser exploits for many years, simply because the complexity of its interaction, of the objects it creates, and automatically garbage collects, and automatically references in many complex ways, has in fact been a boon to the attacker. It has been co-opted by attackers. Any automated action by the system could be co-opted so, and you really, really need to study those emergent behaviors and their complexity and their adversarial reuses. It's not the first time when a thing thought to be a security measure turned out to be the attacker's deputy. And I think this is the final question because we're out of time. Are these tools at all valuable in attribution of who is attacking? Again, my answer would be most likely yes. Attribution is a hard problem because it's very easy in this domain to make things not what they seem. In fact, the very basic steps after an exploit are to make the system seem something other than it is now with the attacker's additions to it. So that kind of fog of war, tools fighting tools, think back to the Grand Cyber Challenge, where a computer was protecting against computerized attacks, are a hard problem. But then, of course, there are also answers to it. Humans have patterns. Humans have tradecraft. Schools of thought have patterns. Those patterns are discernible in their product, be it programs or be it exploits. There are many ways of operating modern infrastructure which create a signal that could be used for attribution. And that, again, is an important field of study. I might say it also belongs to emergent behaviors. And emergent behaviors of computing systems, behaviors that are there, but we don't expect and yet can trigger reliably, are in need of a science of their own, a science of insecurity from which the science of security could spring. Thank you.